Hi guys, we're going to come back here again. Now we're going to talk about the two different types of polygons that we're going to study. And most of the time we're only going to study convex polygons, but we also have what's called concave polygons. And one way that I remember this is from my junior high science classes. It was really cool because I'm sitting there and we talked about convex mirrors. And a convex mirror is a mirror that bows out and reflects outward. An example of that would be like if you're in a gas station and you go in for, or a convenience store, and you go in and you look up and you see that big mirror in the corner. Well, that's used because it's a convex mirror. It's outside. The clerk can see more to make sure no one's shoplifting or goofing off in the store or whatever. A concave mirror is a mirror that goes on the inside. It caves in. And it would look something like this. And then when it caves in, it actually causes focusing of the beams to a central spot. Now, you don't really care about the focusing of the beams. It's more the shape of the mirror that you care about. It caves in. Those are flashlights. Look at a flashlight. They cave in. That helps make focus the light better. So those are going to be kind of some cues that we use to memorize the names of these. But another thing that we have to know is what a diagonal is. Now, I didn't write this as a formal definition, but here we have a quadrilateral. And a diagonal's definition is that it's a line segment that connects the non-consecutive vertices of a polygon. Now, consecutive means the one that goes with the endpoints here. So these would be consecutive. But if I start here at this point, the non-consecutive diagonal would go right across. So it goes across the room like I'm going diagonally. The same way here. So this figure would have two diagonals. So it's pretty simple. So I'm going to use that to define what a convex polygon, and by the way, let me draw a little arrow there so everyone knows what we're talking about. That's a diagonal. All right. Now, we can go through and get a convex polygon. It's defined based on that. A polygon is considered convex if it has no diagonals with points outside the polygon. Now, here's all these dashed lines. These dashed lines right here in this pentagon are all on the inside. So that is a convex polygon. They're all there. So you can see all of them lightly crossed. Now it's like G goes with its two diagonals. And you can have multiple diagonals for one. Then a concave polygon is like it's caved in. It goes, kind of sinks in on a little bit of sides. It's a polygon that has at least one diagonal with points outside the polygon. So a concave polygon with at least one diagonal with points outside the polygon. And here's an example of this. Here we have this closed figure, but if I draw in the diagonals, look where they're located. They're outside of the figure. Even this one right here has points on the outside. So definitely it's caved in. So if it looks like it's caved in, that's concave, caved in like the mirror that got caved in. Now we also classify polygons by the number of sides, and probably over half of these you already know. But you have to have these memorized. We expect to be able to work with the different types because of it. So with the three-side figure, we know it's a triangle, but we know there's more specific triangles out there, like equilateral, equiangular, scalene, isosceles, right, obtuse. So no, we can be more specific, but this is more the general name that covers all of them. For a four-side figure, a lot of you just yelled square, but that's not the only four-side figures, so we call them quadrilaterals. All right, so you have a quadrilateral, four sides, quad. 5 would be a pentagon. 6 is a hexagon. 7's one that we easily forget. That's a heptagon, and some books call it a septagon. So just know carefully how you're reading it. On number 8, we have an octagon. 9 is a nonagon. 10 is a decagon. And 12 is a dodecagon. And then if you keep getting more and more sides, yeah, you can have specific names, but sometimes it just gets too much. So n, for the rest of this time, is going to be the number of sides. And if you have a large figure, you can actually just go an n-gon. So for instance, if I had 20 sides, I'd call the polygon a 20-gon. It's kind of a shortcut way of getting it across. So it's pretty simple. All right, now let's classify each polygon by its sides and identify it as a convex or concave. So just count 1, 2, 3, 4, 5, 6. So that's going to be what? A hexagon. And it doesn't cave in, so that means it's convex. It's all on the outside. It's bowed kind of out. And the next one we have a 1, 2, 3, 4, 5, 6, 7, 8 sided figure. So that's an octagon. And it caves in, and I can also draw this diagonal on the outside, so that makes it concave. Now, we have another one, and I have a typo on this, so go figure, Mrs. Gregerson has a typo when we're working with these. It's called the Polygon Angle Sum Theorem. Now, it says the sum of the measures of any, now this is where it should be, the sum of the measures of the interior angles of any convex polygon with n sides is the following formula. It's the number of sides minus 2 times the quantity, 180. That works for any of these. We can find it out. And when you think about more sides you get, more and more angles you have, larger and larger the sum. So I'm pretty particular about how you work with these. Now this works for any convex polygon. And so I would be very simple. I'd go write your formula down first, and then do all your work directly below it. So when I'm doing that, I put the 15 in. I got 15 minus 2 times 180. I get 13 times 180. And I get 2,340 degrees. Pretty large sum. Just think about a 100-sided polygon, what type of values you'd get for that. It'd be amazing. So that's part A. Now B, we have an octagon. So n in this case is going to be 8. So I still plug my formula down and I go directly below it. So I go, all right, we have 8 minus 2 times 180. So I get 6 times 180. And we get 1,080 degrees. Pretty easy thing to do. Now think about this, works for a triangle. If I go 3 minus 2, that's 1. 1 times 180 is 180 degrees. So this still works also for triangles too. So let's go to the other side and we'll finish this one up. Now it says find the missing angles. Notice I have a pentagon over here and I'm missing one angle. Well, to find the missing angle, I'm going to have to use my previous theorem, the fact I know the sum of the angles. So I can use this formula for the sum of all the interior angles to find what's missing. So I go 5 minus 2 times 180. Should be 540 degrees. And then I can do the sum of all of these angles together. So I'll go x plus 91 plus 80 plus 100 plus 160 equals 540 degrees. And so then when we do that, you then go ahead, and I'm sitting there, I have to get my calculator out here real quick. I do believe here we got 91 plus 80 plus 100 plus 160. And I did something wrong on my calculator. 91 plus 80 plus 100 plus 160, because my mind's not working today. It's 431. So x plus 431 equals 540. So x would be 109 degrees. But notice I had to find the sum of the angles first. Alright, now we're going to do the same thing for B. I have to find the sum of the angles first. Now most people have, for a quadrilateral, the sum of the angles memorized. But if not, you can always use the Polygon Angle Sum Theorem. So I go 4 minus 2 times 180. Get 2 times 180. It's 360 degrees. So that's the sum of the angles. So here's the sum. And then we add them all together. So we get x plus 48 plus 71 plus 112 equals 360. So I get x plus 231 equals 360. X is going to be 129 degrees. Now, this is on the test, so don't forget to study it.